Hello, I'm Professor von Schmohawk, and welcome to YU. In the previous chapters, we saw how to simplify expressions with multiplied exponential terms by adding the exponents of terms with like basis, and how to simplify terms with divided exponential terms by subtracting the exponents of terms with like basis. In this lecture, we will use these rules to simplify expressions containing a variety of exponential terms with different bases which are multiplied and divided. Our goal will be to write these expressions in their simplest possible form. We will do this by combining all terms which have the same base. For example, in this expression there are 2 terms with a base of 2, 3 terms with a base of x, and 2 terms with a base of y. After we have done this, if we are left with any terms with negative exponents, we can change the exponents to positive by moving those terms from the numerator to the denominator, or vice versa. When combining terms with the same base, which are multiplied and divided, we can first add all the exponents in the numerator and add all the exponents in the denominator, and then subtract the denominator exponent from the numerator exponent. Or if we like, we can add all the numerator exponents and subtract all the denominator exponents in one step. Now let's try simplifying the expression with several different bases that we saw at the beginning of the lecture. We'll start by combining all the terms which have a base of 2. We first add an exponent of 1 to the term without an exponent so that we can subtract exponents. Then, subtracting the exponent of the denominator term from the exponent of the numerator term, we get 2 to the negative 3rd power in the numerator. Since this term has a negative exponent, we move the term to the denominator and switch the sign of the exponent to positive. Since 2 cubed is equal to 8, we will write it as 8. Next, we will combine all the terms with a base of x. We first add an exponent of 1 to the term without an exponent, and then subtracting the exponents of the denominator terms from the exponent of the numerator term, we get x to the negative 2nd power. Since this term has a negative exponent, we move it to the denominator and switch the sign of the exponent to positive. Next, we combine all the terms with a base of y. Subtracting the exponent of the denominator term from the exponent of the numerator term, we get y to the 1st power, which can just be written as y. Since there is only a single term with a base of z, we add it to our simplified expression unchanged. However, since the z term has a negative exponent, we move it to the denominator and switch the sign of the exponent to positive. The expression is now written in its simplest form. In our next example, we will simplify another exponential expression with several different bases. At first glance, it appears that we only have one term with a base of 2. However, since 8 is equal to 2 cubed, we can temporarily write it that way so that we can combine both terms. Subtracting the exponent of the term in the denominator from the exponent of the term in the numerator, we get 2 to the 1st power, or just 2. Next, we combine the terms with a base of x. We first add an exponent of 1 to the term in the numerator without an exponent, and subtract the exponents of the denominator terms. This gives us x to the 0 power. Since this is the same thing as 1, we can eliminate this term completely. Next, we combine the terms with a base of y. Subtracting the exponent of the denominator term from the exponent of the numerator term, we get y to the first power, or just y. Since there is just one term with the base of z, we add it to our simplified expression unchanged. However, since the z term has a negative exponent, we move it to the numerator and switch the sign of the exponent to positive. The expression is now written in its simplest form. In the previous example, we started with an expression written as a fraction, and in the process of simplifying the expression, the denominator disappeared. This often happens when rearranging terms in an expression, as we sometimes end up moving all the terms to the numerator. But how can a denominator just disappear? Here is what actually happens. When we moved the denominator term to the numerator, we actually took a shortcut, combining several steps. The first step was to factor out the denominator term from the rest of the expression. This left an expression with a denominator of 1. We then used the rule we discovered in the previous lecture to convert 1 over z to the minus 2 to z squared. We then multiplied z squared with the rest of the expression to combine everything back into one expression. Since this expression had a denominator of 1, it could be eliminated. So whenever we move all the terms out of the denominator, we are actually left with a denominator of 1, which we can then eliminate. Likewise, sometimes when rearranging terms, we end up moving all the terms out of the numerator. In this case, we must add a 1 to the numerator. But why? Just as before, when moving the numerator term to the denominator, we actually combine several steps into one action. The first step is to factor out the numerator term from the rest of the expression. This leaves an expression with a numerator of 1. We then use the rule from the previous lecture to convert the term to 1 over that term with the sign of the exponent switched. Finally, we multiply to combine everything back into one expression. So whenever we move all the terms out of the numerator, we are left with a numerator of 1. So far, we have learned rules for multiplying exponential expressions with the same base and dividing exponential expressions with the same base. In the next lecture, we will learn what happens when we raise an exponential expression to a power.